This is the third and final video in the stoichiometry unit. And you can see there's just one learning target here. We want to be able to calculate theoretical and percent yields. As far as key ideas and definitions, just three definitions here dealing with the learning targets here. A theoretical yield, I don't know if I spell it right, theoretical yield is a term that we've used once or twice before, more dealing with lab work, but it is simply the maximum amount of product that can be obtained in a reaction. And this is always determined by the limiting reactant. Determined by the limiting reactant. As we have seen in our limiting reactant problems, once the limiting reactant runs out, that is when the reaction stops. So that's why it determines how much product that we can possibly get. And when we say maximum amount of product, what that simply means is if in fact the limiting reactant does completely run out, and if we're able to collect absolutely every bit of the product that is formed, and if we were to find its mass, that would be how much we would get. That would be the maximum amount. Another term we need to be familiar with is the actual yield. And the term itself, I think, tells you what it is. It is the actual amount of product that is obtained in a chemical reaction. This is not something that you can calculate. This is something you simply measure once you've done the experiment. You do the lab, do the reaction, you collect your product, you put it on the balance. Whatever mass you have, that is your actual yield. The other term, the last term we need to be familiar with, is the percent yield. And this is a calculation that we have done in the past. It is simply calculated by taking the actual yield divided by the theoretical yield, and we multiply by 100. That is equal to our percent yield. So the more efficient your lab is, the closer you get to the theoretical yield, then the closer this will be to 100%. And as we've seen in the past, it would be impossible to get anything more than 100%. Because you can't get any more than your theoretical yield. Alright, looking at the example problems here. Let's just see how these ideas apply. First one is we are asked to consider this reaction, the potassium chromate and silver nitrate reaction. You can see the products there. We are asked, what is the theoretical yield? So remember, that's the maximum amount we could get. So what's the theoretical yield of silver chromate if 0.500 grams of silver nitrate reacts with excess potassium chromate? Well, the fact that the potassium chromate is in excess, that tells us that the silver nitrate, that has to be limiting. So I'll just jot that up here above silver nitrate. The fact that we're not given a mass of potassium chromate, we're specifically told it's in excess, that tells us the silver nitrate is going to run out first. Well, this problem here, this is just a basic gram, mole, mole, gram problem that we've been doing for a while now. Because we already know silver nitrate is limiting, we already know the 0.500 grams of silver nitrate is limiting, we don't need to figure out what the limiting reactant is. So we know that the silver nitrate, that will determine how much product we can get. So we're just going to convert from silver nitrate, mass of silver nitrate, into the mass of silver chromate. So we need a molar mass of silver nitrate, which is 169.88 grams AgNO3 for every mole AgNO3. Grams cancel. We now have moles. Now we need to use our mole ratio. We can see 2 moles of silver nitrate react for every 1 mole of silver chromate. Notice the equation is already balanced for us, so that's why we can just go ahead and use the mole ratio there, because it's already a balanced equation. And then last, we need a molar mass for silver chromate, which is 331.74 grams Ag2CrO4 for every mole. Ag2CrO4. Moles cancel, and we are done with that problem. Just need to plug it into a calculator, and I've already done this. This is 0.488 grams Ag2CrO4. Okay, again, that is the theoretical yield, meaning if all of our reactant, if all of our limiting reactant actually does react, and if we were able to collect every single bit of product, that's how much we would get. Now, question B says, if the reaction yields 0.455 grams of silver chromate, meaning this is the actual amount that we get, this is the actual yield, what is the percent yield? Well, if we look up at our equation up above here, we can see we're just going to take the actual yield divided by the theoretical yield. So 0.455 grams is what we actually get, divided by the theoretical yield that we just calculated in A, 0.488 grams. We multiply by 100. So let's see what that is. I haven't done this calculation yet. So 0.455 divided by 0.488 times 100 equals, let's see, 3 sig figs, it's 93.2% yield. 0.2%. There it is. Alright, next example, over to the back here, asks us to consider the reaction between zinc and hydrochloric acid. Notice the equation is already balanced for us. And we are told if 25 grams of zinc are reacted with 23.2 grams of hydrochloric acid, what is the theoretical yield of zinc chloride, ZnCl2? Well, in this case, we don't know what the limiting reactant is, so we need to determine what that is before we make a determination what the theoretical yield of zinc chloride is. So just like we've done before to find a limiting reactant, we need to convert our masses of reactants, into moles. So gram to mole conversion for zinc. Molar mass of zinc is 65.39 grams of zinc for every mole of zinc. Grams cancel. 25 divided by 65.39, that gives 0.382 moles. 2 moles of zinc. We need to do the same thing for the hydrochloric acid. We have 23.2 grams of HCl, and we need the molar mass is 36.46 grams of HCl for every mole. HCl, grams cancel. And this gives us, let's see, we have 23.2 divided by 36.46. That is 0.636 moles of HCl. Alright. Now we need to set up a chart to find what the limiting reactant is. We have zinc plus 2 moles of HCl. That gives zinc chloride plus H2. We start with 0.382 moles of zinc and 0.636 moles of hydrochloric acid. I can see from the balanced equation that we need 2 moles of HCl for every 1 mole of zinc. So I'm just going to do a quick calculation here. If I have 0.382 moles of zinc, so I'm going to take 0.382 and I'm going to multiply that by 2, I would need 0.764 moles of HCl to go along with it. Well, notice I don't have that. I have less than 0.764, so that tells me the HCl is going to be limiting. So I know that all 0.636 moles of HCl will react. That gives me 0 moles of HCl. For the zinc, it'll be minus 1/2 times that. So it'd be 0.382 minus 0.5 times 0.636. That gives me 0.064 moles left over. Then as far as what we're concerned with here, notice we're asked to find the theoretical yield of zinc chloride. So I'm just going to fill in that part of the chart here. Notice this is a 1 to 2 ratio between zinc chloride and hydrochloric acid. So we are going to form 1/2 times 0.636 moles. So 0.5 times 0.636. That gives us 0.318 moles of zinc chloride. And then the hydrogen we're really not too concerned with here. We could go ahead and fill it in though. Notice it's the same ratio as the zinc chloride, so we'd also get 0.318 moles of hydrogen. But to answer the question, what is the theoretical yield of zinc chloride? We just need to convert our mole value. We know we're going to get 0.318 moles of zinc chloride times, now we just need to multiply by the molar mass of zinc chloride, which is 65.39 plus 2 times 35.45. That gives us 136.29 grams of zinc chloride for a mole of zinc chloride. So just doing the multiplication. That gives us 43.3 grams ZnCl2. And there's our theoretical yield. Alright, next question. Calculate the percent yield if you collect 31.7 grams of zinc chloride from the reaction. Well, we actually get 31.7 grams, so that's our actual yield, divided by the 43.3 grams that we calculated as our theoretical yield, multiply by it 100. So just doing the division, this gives us 73.2% yield. There it is. Alright, the practice problem, I pause the video and try to work it and then see how you did. So we are told to perform the following reaction, you drop a copper wire weighing 1.62 grams in a solution containing 0.850 grams of silver nitrate. You collect 0.262 grams of silver as a product. What is your percent yield? Notice here you're not given a balanced equation, or an equation period. Looks to me like though the question was originally written to give you one, because it says to perform the following reaction. We can still figure out what it is though. Looks like our reactants are copper, Cu, and silver nitrate, AgNO3. This reaction should look familiar to you, considering we just did it in the lab last week, or maybe a couple weeks ago, depending on when you're watching the video. Recall that the products of this reaction are copper 2 nitrate, CuNO3 and silver. And then to balance the equation, we would need 2 moles of silver nitrate and 2 moles of silver. Alright, now we just need to convert our masses of reactants into moles, because we need to determine what our theoretical yield is here. And to do that, we're going to need to find the limiting reactant. So doing our conversions here, I'll do those off to the side. We have 1.62 grams of copper. Molar mass of copper is 63.55 grams of copper for every mole of copper. So 1.62 divided by 63.55, that gives us 0.0255 moles. That's what that is. So I'll fill our chart in here initially. We have 0.0255 moles of copper, and we have 0.850 grams of silver nitrate. Let's see, we already used the molar mass of silver nitrate before on the worksheet. I'm going to flip back and look at what that is. That was 169.88. So 169.88 grams AgNO3 for every mole. AgNO3. So 0.85 divided by 169.88. That gives us 0.00500 moles of silver nitrate. What I get there. Alright, so to determine the limiting reactant, you can see here that we need 2 moles of silver nitrate for every 1 mole of copper. So we need more moles of silver nitrate. However, when we look at what we actually have, we have fewer moles of silver nitrate to start with. So that's going to be limiting because there's just not going to be enough to react with all the copper. So all 0.00500 moles of silver nitrate will react. And then for copper, it's going to be minus 1/2 of that because it's a 1:2 ratio. So minus 0.00500. That's getting a little small there. Let's see if I can correct that. Alright, so for the silver nitrate, we have none left over. For the copper, we have 0.0255 minus 0.5 times 0.005. And that gives 0.0230 is what we get there. So we've determined that the silver nitrate is limiting. Even though we're not actually asked to find that, we do need to make that determination. And then we're told that we collect 0.262 grams of silver as the product. And we want to know what the percent yield is. Well, that means we need to know what the actual yield is. So just for silver, we don't really need to worry about the copper nitrate. We start with 0 moles of silver. Looking at our mole ratio, 2 moles of silver are produced for every 2 moles of silver nitrate that react. So the change is just going to be plus 0.00500, just going to match the silver nitrate. So at the end, we should have 0.00500 moles of silver. So to find our theoretical yield, we just need to convert that number of moles into a mass. The molar mass of silver is 107.87 grams of silver for every mole of silver. Moles cancel. This gives us 0.539 grams of silver. This is our theoretical yield. It's our theoretical yield. To find our percent yield, we just need to take the actual yield of 0.262 grams of silver divided by the theoretical, 0.539 grams of silver, times 100. So 0.262 divided by 0.539 times 100, and this gives us 48.6% for our percent yield.